Members which make up a typical domestic building consist of a column, beam, a girt, a mullion, and bracing. These members are mandatory in order to make a strong and economical building, such as a portal framing structure in the video. Connections between these members consist of an apex connection, a knee connection, and a base connection. To design these members and types of connections, it is important to calculate the loads which will affect the building throughout its lifespan. These loads are dead load, live load, wind load, and possibly earthquake or snow load.
When designing a structure for wind loads, there are a number of variables that engineers must account for, including the wind region, wind terrain category, the shielding of the structure, as well as the topographic effects. Furthermore, the structure must be designed for wind in both the inward and outward directions, the pressure and the suction. The domestic shed that is the subject of this report is in Wind Region A, which is a non-cyclonic wind region. The structure falls under terrain category TC3, with numerous closely spaced obstructions surrounding the structure. By using the variables of wind region and site conditions, engineers can refer to the tables in AS 4055 to determine the wind classification for the structure.
The first steps in designing the purlins are defining what wind region, terrain category, topographic class, shielding class, and the wind classification the shed lies in. Most of these values and classifications were provided on the assignment sheet or found using the AS 4055. Once these values were found, the serviceability and ultimate limit state could then be calculated, which is needed to calculate the wind pressure and suction forces on the shed. Before selecting the final purlin members, the dead and live loads of the building also need to be figured out. The dead loads of the shed compose of roof sheets, ceiling, insulation, services, and an assumption of the self-weight of the purlin. These figures could be found on company specification documents and on the AS 1170.1. The live load figures were also found under Table 3.2 of the AS 1170.1. Finally, the load combinations in Table 4.2.2 of the AS 1700.0 were used to demonstrate if the original purlin members selected were usable, which in the report's demonstration were not. Therefore, a new purlin member had to be selected. Once the strongest yet most economical design member was selected, it was checked to see if it met all serviceability requirements.
To develop a further understanding and gain real-life valuable experience, a site visit was arranged for all Structures 2 students to the structural engineering laboratories at UniSA's Mawson Lake campus. There are two primary reasons as to why the site visit was conducted. Firstly, to see firsthand a completed superstructure that was built using the construction techniques that we've been learning about, and also a batch of concrete was made and a concrete slump test was conducted, demonstrating the theory that has been taught in the superstructures component of this course. At Mawson Lakes, we visited the L building, which is extremely similar to the one that we will be designing for this project, so it was very useful to be able to see the design processes having been used on a superstructure in person. The site supervisor pointed out that perhaps the purlins are spaced too close together. Although this is not a structural issue, it would suggest that the building was not quite as economical as it could have been. Upon completion of our time in the L building, seeing a roof shed and observing how the structural members are composed and interact with one another, we moved to the structural testing facilities. In the testing area facilities, there was a large focus on the substructural elements of a domestic shed. A concrete mixture was made to perform a concrete slump test, which is a procedure performed by structural engineers to measure the consistency of concrete before it sets. In conclusion, having the opportunity to visit and go inside the L building on the Mawson Lakes campus was a highly practical method of seeing how the structural components of a superstructure are composed. To see how the beams, purlins, bracing and cladding are all composed gives excellent context to the purpose of this report and will aid with the design of the domestic shed. Similarly, having the opportunity to observe not only how concrete is mixed, but how it can be measured will assist greatly with our understanding of structures and their design processes.
Before starting the bracing design, the ultimate limit state figure calculated in the wind load section needed to be calculated with the net pressure coefficients found in the AS 4055 to find the wind pressure and suction hitting the shed. This, along with half the shed's surface area, could then be used to find the pressure and suction forces in kilonewtons. It is important to note that the bracing layout of the roof included a strut in the middle of the 8 metre span, meaning that there were two sections of cross bracing at a 4 metre span. With all this in mind, the maximum tensile and compression forces could now be calculated. The reaction force was firstly found by dividing the equilibrium of the pressure and suction forces by 2. Next, trigonometry and algebra was used to calculate the tension and compression forces in both diagonal bracing members and in the struts. 50 by 50 by 3 equal angle sections were used for the diagonal members in tension, while square and rectangle hollow sections that met both the compression forces and buckling requirements were used for the members under compression. To find the forces in the wall bracing, it was assumed that the equilibrium of all forces equaled 0. Therefore, a connection point was selected to calculate both the forces going in X and Y direction. Once these were found, it was a matter of using trigonometry again to find the forces in the diagonal cross bracing. 50 by 50 by 3 equal angle sections were also used for the wall bracing in tension. It is important to note that 2 different designs were undertaken in the report due to the different height at each end of the shed. Although the final calculation values of each design were different, the method of the calculations were the same.
The first step for designing the rafters in the shed is to calculate all of the loads that they will support, including the dead load, live load, and the wind load. The dead load consists of a number of different factors, including the roof sheeting, the self-weight of the purlin, the ceiling, insulation, service weights, and self-weight of the rafter. To determine the live load for the design, we must refer to Table 3.2 of AS 1170 for other roofs, and the following formula is given. Uniformly distributed actions equals 1.8 over the area plus 0.12, not less than 0.25 kPa. The next step is to determine the most adverse uniform distributed load combination. Then, we need to determine the moment using the loads. This is done using the following equation. Moment equals W times length squared over 8. From this, we use the capacity tables to select an appropriate rafter for the shed. The design capacity tables provide structural engineers with the ability to select structural support members that are both safe and economical. By choosing the rafter member that intersects the line given the moment capacity and effective length, the suggested beam will be strong enough to support the structure without being unnecessarily strong. This process is then repeated for the end rafters, as they will be different to the central rafters. One of the key findings was that the central and end rafters will in fact be different, despite the fact that we initially thought that they may not be.
A column is a vertical member which transfers the loads from the above members down to the foundation of the structure. Columns support the ceiling above and therefore allow the span distance for the members above the ceiling to be significantly increased if designed accurately. Compressive axial loads are carried down through the column members from the pin connections between the beams and the columns. Step 1 was to calculate the tributary area, which equaled 24 meters squared. Step 2 was the dead load calculation, where I was able to use previous calculations plus an added central rafter self-weight, which summed up to be 2.917 kilonewtons. Step 3 was to find the live load, which could not be less than 0.25 according to the AS 1170.1 table 3.2. The live load then equaled 6 kilonewtons per meter, found by multiplying 0.25 and the tributary area. Step 4. Wind load calculation, which was found the M max and the M1 using inward and outward pressure of the building from previous calculations. However, the outward suction can be ignored in this scenario. Step 5 found that load combination 4 was the most severe. Step 6 designed the member with 100 UC 14.8 member, which was verified to be safe but not economical. However, it was the smallest selection. Step 7, moment calculation, which furthermore illustrated that the selection was correct. However, the additional capacity in the member verified that it was not economical.